Okay, so this is the second part of lecture G1 on randomness and chaos. So as we talked about in part 1, there are these two phenomena that are often confused in the kind of popular language, randomness and chaos. Randomness, as we talked about in part 1, is a modeling tool that simplifies model building, whereas chaos is an apparent randomness that sort of emerges from systems or models of systems that are fundamentally not random. And so randomness makes modeling easier, but chaos makes modeling or makes using models a little bit more difficult. So we talked about randomness last time and how we use it in models, and so now we're focusing on chaos. So a simple definition for what chaos is an extreme sensitivity to initial conditions. So we'll see what we mean by that. So a very common example when you do system dynamics modeling, maybe I'll get rid of me for a bit here, is this fisheries model. So as a simple fisheries model, here's a diagram I borrowed from Moorcroft's 2015 textbook on system dynamics modeling. And so if you were to simulate a fishery like this one that has this net regeneration curve, which is kind of hump-shaped like this here, then you end up getting curves that look like this. And so this is the exact same system, but I've started with different numbers of fish initially in the fishery. So if you initially have, a small number of fish, say, 100 fish versus 150 versus 300 fish, then you get curves that look slightly different initially. But over time, they end up converging to the same spot. And so in this case, they all end up going to carrying capacity. So the outcome where the fishery is at carrying capacity, we might view that as an attractor. That might be a term we use, or an equilibrium, or sort of the steady state value of a fishery. And the fishery might have multiple. The fishery, we know in this particular fishery, if you start with 0, it'll hold 0 forever. And so that is also an equilibrium, but we know it's not an attractor because if you add one fish, then it'll rush away from 0 and it'll eventually, if we assume fish were clonal, if you add one fish, then eventually you'll end up hitting carrying capacity. So there's these equilibria that have this interesting ability to attract trajectories to them, so that if you were way off in the distance, so many years down the line and you're sitting at carrying capacity, there's no way to look at the carrying capacity that you're sitting at and know how the kind of system started. So your initial conditions start with some individuality, but they lose their individuality over time. Okay, so we have different initial conditions, and the system is attracted to the same state. The long-run behavior is insensitive to those, and in the long run, it's impossible for us to tell the difference between any two trajectories. That's kind of what we're shooting for here. All right, now let's look at a different system. So this is this Mackey-Glass system, named after two people who came up with it. It looks like a relatively simple system when depicted in a system dynamics model like this one. It has a single stock x, or if you're more mathematically inclined, a single state variable x. It has a little bit of an outflow here, which depends on x, and it has an inflow, which depends on a delayed version of x. The mathematical expression here represents this whole system. So this dx dt is effectively the net inflow into the system. So you can see that here's the outflow component. So you can imagine inside this outflow, you could have this gamma parameter. So gamma times x would be inside there. And then there's this delayed version of x, which I'm calling x t minus tau. So tau is a version of x from tau seconds ago. And so in VinSim, you would implement this with a delay fixed. There's a similar thing to do in Insight Maker, where you can say, I just want whatever x was doing exactly this amount of time ago, an exact copy of that. And so I can create a delayed version of x, and then I can run that into the inflow, and then this inflow formula is basically going to have beta times the delayed x divided by 1 plus the delayed x raised to this n power. And I can sort of substitute those with these parameter values over here. So let's just do that to make it look a little simpler. And so I end up getting with a system that looks like this one. So this looks maybe a little complicated, but it really doesn't look very different than many of the complex one compartment or one stock, one state variable models that we've seen in the class. And so the point of this Mackey-Glass system is to show that even with simple systems like this one, if you have sort of the right nonlinearities in these formulas, then you get some interesting behaviors out. And so let's see what those interesting behaviors will look like. So if I hit run on that simulation, and I'm going to do the same thing I did with the fisheries, I'm going to start with 3 different initial conditions. And so it's hard to see exactly where I started, but they're kind of over here. They're all around 1. So you could imagine maybe I started with 1, 1.1, and 1.05. I don't remember exactly which initial conditions I started with here, but small differences from 1. Now initially, unlike the fisheries case, the system looks very, very similar. So the blue, the red, and the green trajectories almost sit right on top of each other. But then over time, notice that the blue, red, and green trajectories start doing different things. They are still distinguishable way out here at higher times. And so I started with different initial conditions, and if I magnify, I see that initially they start together, and then they start separating. And if I look, the patterns don't even quite match. It's not like they're just delayed versions of each other. If I look, this blue pattern, it kind of goes up, it goes down, and then it has this like tiny peak and then flat area, whereas this red one, it almost looks like it's oscillating with this tiny little double peak and another tiny little double peak and another little tiny double peak. And then this green one looks almost like it's got 3 peaks, and then it does something else, and then there may be 3 peaks again. So I get very different curves out of this, even though they all started doing basically the same thing. And if I go a little bit farther out, so if you look at my time scale here, even after long amounts of time, you can disregard the year. That's sort of just a poor choice of units on my part, but whatever, we don't know what this process might be modeling, so maybe year would be appropriate. Then you see that these trajectories maintain their individuality for long periods of time, and then sort of actually will continue to maintain their individuality. So the kind of lesson here is that we already know that from earlier in the course that if you have a negative feedback loop, like a generic one like this with delay, then you can get interesting oscillatory behavior, or you can get these sort of damped oscillations, like in a shower example where you're trying to control the temperature of the shower. If there's delay in when you turn the knob on the shower and hoping to get hot water, and you don't immediately get the hot water, you might turn the knob farther and then get the hot water you requested a little earlier, and then it will continue to increase. So now it's going to be too hot. So then you might turn it down. And so that's could give you these interesting delays, which will create these kind of oscillatory behaviors. Now, if you know that there's going to be these delays, you can kind of resist the temptation of turning the dial too far forward or too far backward, and maybe you end up getting something that looks more ideal like this. But in reality, when we all get in the shower and we don't exactly know what the delay is going to be, we might just maybe not get in the shower, for the first 30 seconds or so, or you might just tolerate the cold water, and so you end up getting maybe something that looks more like this. And so you can get a wide range of behaviors out of negative feedbacks with delays, and even full-on oscillations. Now, what the Mackey-Glass system shows us is that if you have some very interesting nonlinearities combined with these negative feedback with the delays, then those oscillations get far more complicated, and you get something that doesn't even look like an oscillation, but it still has a lot of character to it. So in other words, you get chaos. And so nonlinear feedback with delay can lead to chaos, where chaos, again, is an extreme sensitivity to initial conditions. So that's one way we can get chaos. And so I normally ask if there are questions here, but I'll sort of move on then to, are there other ways we can get extreme sensitivity to initial conditions? Is delay necessary? Can I get chaos even in systems without delay? And so I'm going to turn to one of the more famous chaotic systems, the Lorenz system. So this is a simplified mathematical model of atmospheric convection. So if you'd like, you can think of it as a simplified model that maybe a weather forecaster would use in order to predict what the weather might be. And if you look at it, it's so here on the right-hand side, this is the mathematical expression, 3 coupled ordinary differential equations. On the left-hand side, I've just drawn it out in VinSim as 3 different stocks, each with their own inflows. Now, there's minuses here, so I could have drawn these with outflows and everything, but I just sort of bundled everything up into 3 different outflows. And then there's 3 parameters, sigma, rho, and beta, sigma, rho, and beta. Which I could end up fixing with these numbers. And so maybe we'll just do that to clean up this. And so there I've got all those plugged in here. So I can implement this thing right here. And it is a little complicated, but if you think about it, it really doesn't look too much worse than any of the other 3 or more compartment models that we've seen throughout the class. This doesn't look much more complicated than, say, an SIR model, for example, from epidemiology. And yet we're going to get some really interesting behavior out. Now, if you go and do this on your own in InsightMaker or VinSim, in order for you to get the right patterns, this is one of the very few systems that we study this semester where you can't use the Euler integration type. So in your model settings, down at the bottom of the model settings, both in InsightMaker and in VinSim, it has a portion where you can set the integration method or the solver method or the type of solver, and it by default will be set to Euler, E-U-L-E-R, and you need to change that to RK4 auto, this Runja-Kutta for auto, which is sort of outside of the scope of the class for me to kind of discuss the differences between these. But to make a long story short, rather than using the kind of fixed compound interest rates of Euler, then this Runja-Kutta solver kind of has more control over how it can make these compounding periods, and it can make them smaller and larger in order to ensure that as it's solving this problem, it doesn't accidentally approximate something as constant when it shouldn't be. So for this particular one, it's a weird enough system that we really kind of need the stronger solver. Okay. So what do we get when we hit play here? So what I've got plotted here, I've got Z that's the compartment, the stock that I've kind of zoomed in on here, but I've also got X and Y here. And again, I've done 3 different initial conditions, which are these 0, 1, and 2. And so X0, Z0, and Y0 are the X, Y, and Z trajectories from one initial condition, and then 1 and 2. And so, so again, there's no randomness in here, and yet I get some really weird looking behavior. And in all 3 of these cases, X, Y, and Z start out looking very similar. So if I look at Z, all 3 trajectories go up to a peak, they come down, and they start this kind of growing oscillations. So this kind of looks like that shower, that it swings down, and maybe you overshoot, then overshoot more, and eventually you've got lots of huge overshoots. But then down here, the 3 trajectories start to separate out. Blue and red start being distinguishable, and then green pops up. And then out here, you can see red, blue, and green are kind of doing their own thing. It's even stronger in this Y one here, where you've got blue coming up, and then it looks like, you can really see there's like interesting peaks in green that you don't see similar peaks in blue until later, and they're totally different peaks. And then same thing down here in X. So again, we're getting this extreme sensitivity to initial conditions and a sort of maintained individuality of those initial conditions and an apparent randomness from a system that doesn't have any real randomness. Now, what the kind of hidden lesson here is that this type of chaos is without a delay is only possible if we have 3 stocks or 3 state variables or a third order system. If you have a second order system, 2 stocks or less, and you don't have any delay, turns out that chaos is not possible for reasons that are outside of the scope of this class. But I welcome you to sort of look into that more. But once you got 3, then you've got chaos that's an opportunity. Now, despite those x, y, and z plotted over time looking like they were very different from one initial condition to another, it turns out if we plot this a little bit differently, then we start seeing similarities across the different initial conditions. So what you're seeing here on the left is on the x-axis I've plotted x, and on the y-axis I've plotted y. And what you're seeing here is a plot where we've gotten rid of time. So this is what we call a parametric plot. And I've sort of said at any particular time, what is the x value at that time and the y value at that time for just one of the sets of initial conditions. So for this set of initial conditions, for each time I plot the x and y value and I end up getting this curve down here. So if I go back to the previous plot here, I might say at 8 seconds, x is this value. Or y is this value up here. So at 8 seconds, y is up here. And then at 8 seconds, x is right here. And at 8 seconds, z is right here. And so I can say then, all right, so I'm going to plot the this x and this y together on that xy plane. And then I can say, all right, if I go a little bit farther, then at 10 seconds, y is here, and at 10 seconds, x is here. And so now I can have a new xy pair that I can plot. And I could connect to the two of those from 8 to 10 in sort of a straight line where every point along that line is every time in between 8 and 10. So that's what we refer to as a parametric plot. And if I do that, then I end up getting a plot that looks like this one, where what this point here at say 1 and I don't know what this is here, let's call it 1 and 5, then that's going to tell me that when x gets close to 1, then I've got a lot of trajectories of y that are close to 5. But over here, when x is close to 10, then I've got some trajectories of y that are way up here higher than 15, and some trajectories of y that are way down here in the negatives, say negative 10 or so. And so this allows me to see how x and y relate to each other. And what's interesting is that, so this is for one initial condition, and this is for another initial condition, and I get roughly the same shape. So across initial conditions, the relationship between variables actually reveals that there is structure here. Although in the previous plot, this looks apparently random, this randomness is just it's actually structure disguised as randomness. And so for this system right here, which we know is fundamentally non-random, it produces something which looks random. In fact, some random number generators, remember part 1, are built off of chaotic systems like these. But in reality, then we can then back out the original deterministic structure, the original non-random structure, if we plot the x and y's together, and you get this interesting sort of shape here. And I can go even farther and actually plot x, y, and z in 3 space together. So this is an image that I borrowed actually from, I think, the Wikipedia page on the Lorenz Attractor. So it's compliments of a guy named Dan Quinn. And so you can see what Dan has done is he's plotted x and y and x and z and y and z, and he's showing us the 3-dimensional shape that is traced out by one of these trajectories. And so the little ball that is sort of moving around this shape here represents, I talked about a parametric plot, that is sort of representing the time trajectory of x, y, and z as they all move together throughout time. So that ball, if you were to pause this thing and then ask what the x, y, z coordinates of that ball were, then that would tell you what the x, y, and z values were for a particular realization of this. And regardless of what initial conditions you start on, you end up tracing out a very similar shape. Although if you were to just look at the x, the y, or the z, it wouldn't quite be clear which shape you were looking at. So this is something that is often called a strange attractor. So we started this thing talking about, like in the fisheries case, the carrying capacity, we could view that as a attractor because a bunch of trajectories go to it. Well, this is a strange attractor. It is a very weird shape that kind of doesn't really match anything, any easy description. It's not a simple oscillation, but it acts like an oscillation would. And so trajectories are attracted to it. Multiple initial conditions will end up always sort of landing on this three-dimensional shape. If we look at any one slice of them, this won't be clear. So likewise, if you were to sample a real system, what this tells us is if I was to sample some nutrient content inside a pond, and I were to sample that over time, and I watched those nutrient content kind of vary, I might think that variance was just noise caused by, some exogenous source. It could be caused by noise in my measurement technique. But if I look more closely and measure additional components of that pond, just like measuring X, Y, and Z, or if I even looked at the relationship of those nutrients now and a little bit later and a little bit later from there, as if the different delayed versions of the nutrients were almost like these different stocks, then I might end up finding a structure like this. And if I found a structure like this tells me that that weird variability I got actually isn't exogenous noise. It's actually endogenous structure. It shows me that it's actually being generated by the dynamics of the system and not like some weird part of my measurement noise or something like that. So the endogenous pattern does not become clear without measuring all these variables simultaneously. And if I infer that my apparent randomness is sort of noise in the measurement of X alone, then that would actually be a mistake in this particular case. All right, so Lorenz, sort of who came up with this this model of this basic atmospheric model, he has this really nice quote, chaos. When the present determines the future, but the approximate present does not approximately determine the future. Now remember, this is a model of the kind of atmospheric processes. Now when you get a weather forecast, you only trust the weather forecast for the next day. You don't necessarily trust it for the next 5 days. Maybe you do, but you know that it's going to start being not very good at predicting things way out. Trusting a weather forecast that's 30 days out, nobody does it because you just can't, we just don't know. And that's actually kind of reflecting this idea that Lorenz kind of captured, and the reason why he kind of picked this atmospheric model is that you can have systems which appear to be fundamentally deterministic, like a model which takes into account all the processes that we think are going on in the atmosphere. But if we guess wrong at what the initial conditions for those models are, although it may not hurt us initially, it's going to guarantee that we're going to diverge from reality in the far off distance. So the approximate presence does not approximately determine the future. If we get things a little wrong initially, they may be a lot wrong in the future. And that's what's kind of being captured here. Okay. So that brings up another phenomenon that you often hear about when people talk about chaos, and that's this so-called butterfly effect. And so the question is, what is this butterfly effect? And so a lot of people misunderstand the butterfly effect as some weird thing that has to do with these chain reactions or something like that. So a lot of people think that the butterfly effect is some weird thing where if a butterfly flaps its wings, then miles away it will somehow cause a weather phenomenon to occur. But that's not what the butterfly effect is. So again, the butterfly effect goes back to what Lorenz was saying about these weather models and these atmospheric models. If you have an extreme sensitivity to initial conditions, then you can think of the real world as one universe and your model is another universe. And if your initial conditions are slightly off, then the predictions in your model are going to be way off the predictions from the real world. And it's not due to model inadequacy, it's due to the fact that you didn't quite get the initial conditions correct. If the weather system fundamentally is that way, then you could imagine in one universe that's identical to ours, except for a butterfly having their wings up or wings down, then in that universe, they may get very different weather patterns. And it's not because the butterfly caused the weather patterns by flapping its wings. It's because that tiny little initial condition of the butterfly's wings being up ended up sort of relating to microscopic differences that accumulate in ways that that have large-scale consequences in the far future. So these chaotic systems have a way of expanding differences to the point where you might think that our universe and that universe would have insignificant difference if the only thing is different is that in that butterfly. But there are processes within that system that will amplify those differences and make them significant again. So that's really what this butterfly effect is all about. All right, so that's all that I have for this segment. If you didn't see part one was all about how we use randomness in order to make our models simpler. And in this part two that we just went over has to do with how chaos is not a random effect, and it's not something we want or we want to add. It's something we sometimes get out, and we have to be very careful when we work with these systems that have these chaotic dynamics.